Okay, so hello everyone. Welcome to this session. So today we start a new topic, which is the global observables. And today's talk is measuring global observables in the star experiment by Grigory Nigmatkulov. So it will be a 1 hour talk followed by a question answer session. And so during the talk, it is preferable that if you have questions, you type it in the chat box and we will keep track of those questions. And then maybe at the end of the talk, we will narrate the questions to Gregory for his response. Unless you feel that it's some urgent query and you would like to ask the question instantly, then you might go ahead and ask it. But otherwise, it would be preferable that we do the question answer session at the end of the talk. Okay, Gregory, over to you. Yeah.
Okay. First of all, of course, I would like to thank organizers for giving this brilliant opportunity to give my sort of personal view on what is very important or some selected results which are quite important, at least that I think they are quite important. And I will try to convince you during today's seminar about what is interesting and what future directions could be performed or looked at in the nearest future. Oops, can you still see the slides?
Yeah, now it's
okay. And what I would like to start from is this brilliant pictures on the background, and that is an event display of the STAR experiment. And here we actually can look at several very interesting properties which are quite famous. Of course, one in the very bottom, on the right bottom side, is the sketch of the heavy ion collision in the most central heavy ion collision when two ions hit each other basically very hardly, and many particles produced, and we reconstruct all these particles, charged particles, and this is how this sort of a puzzle looks like, because it's indeed a puzzle. We need to register each particle and try to track it back to the collision region. And this is very interesting and typical sketch that one can see. In addition to that, because there are a lot of interplay between various types of physics, here you can see, for example, at the top slide, this is somewhat called cosmic rays. When we actually measure cosmic rays, which are coming from from space to the nearest part of the atmosphere, and they interact, and particles produced in these interactions, they fly towards the Earth, and during this decays of some of those particles, basically we measure a lot of muons in the surface of the Earth. And this also is interesting thing, because star is actually placed on the surface of the Earth, and we are not like the LHC, which is underground. We are actually exactly on the surface of the Earth. And you can also see a lot of electrons, which are results of the interactions, and they got bended in the magnetic field. And the magnetic field is, of course, an important thing to measure, to basically measure to estimate the momentum of the particle, looking at the how strongly this trajectories are bended. Okay, so now actually coming to our most important things or field, basically the whole relativistic heavy ion field. We would like to measure something which is called quark gluon plasma. So what the quark gluon plasma is. From particle physics, we actually know that quarks and gluons are the tiny little building blocks from which normal particles like protons, neutrons, and other particles consist from. And those quarks and gluons, quarks are basically tightened together by gluons, and this is known as a strong nuclear force, which is the most powerful force among the four fundamental forces in the nature. At least for we know four, probably there's something else, but for now we think that there are four forces: strong electromagnetic, weak interaction, and also a gravitational interaction. So here, from particle physics, we know that strong forces are such strong that actually we cannot find quarks and gluons in a free state somewhere. They always bound together inside the composite particles. And there was a theory in the mid-60s, which and 70s, that actually said, okay, as soon as we can produce quarks, and we actually can find these quarks via deep inelastic scattering experiments, when, for example, electron is scattered, high energy electron is scattered on the proton, inelastically, basically we can measure the individual partons, quarks or gluons. Now the question is it possible to create such a matter that would release the quarks and gluons at least for some time or in some large distances? And at some point it was proposed that in the case of relativistic heavy ion collisions, we can actually create such type of matter, which was called quark-gluon plasma, in which the quarks and gluons are sort of semi-free. At least originally it was expected that they are almost do not interact for some amount of time, basically, and plasma comes exactly from this low interaction rates, which turned out to be not as trivial as expected. But anyhow, the term quark-gluon plasma is basically standard term for relativistic heavy ion collision field. And reasonable question would be also where we could find such type of matter, because it's indeed very different from the normal nuclear matter. And the answer is that in principle, one should expect that such type of matter could exist at the first moments of the our universe expansion, basically right after the Big Bang, when we had when the universe consisted from quarks, gluons, leptons, photons, and so on. But during the expansion, of course, it would look like the large distances, because the expansion of the universe was quite fast. For some amount of time, the universe was supposed to be in such a state of matter. And also nowadays, we could try to search or look for the quark-gluon plasma in the collisions of the neutron stars or inside the neutron stars directly, if those are quite heavy. And the reason for that is that we, in principle, can compress nucleons to such high pressures that gluons and quarks will go inside each other from different nucleons, and then basically will create such state of matter inside the neutron stars. So that is how we could search for that very specific state of matter in the universe. However, of course, we cannot basically we cannot create another Big Bang in somewhere on Earth. And also another important thing is that it's not quite easy to create neutron star here. However, instead of creating such exotic objects, what we can do, we can collide heavy ions, not just heavy, but various ions, and create such a matter in the laboratory and see how this quark-gluon matter, or whatever, let's call it quark-gluon matter or quark-gluon plasma, will expand and what properties will it have. And depending, of course, on the properties of this quark-gluon matter, the evolution, or the collision evolution, or you can think about it as about the universe evolution, might be a bit different. So since I have already introduced the collision evolution between the mentioned collision evolution, let's look at the typical heavy ion collision, relativistic heavy ion collision. So in general, in a normal state, our nuclei, they have some shape, and this shape is basically dictated or could be described by the Woods-Saxon distribution, which defines the nucleon density inside the nucleus. However, when we accelerate nuclei, those nuclei got compressed due to, basically they have a Lorentz compression, and one can imagine the nuclei as a basically collision of two sort of pancakes. And then, of course, some magic happens, and this magic, at some point it would be called magic, but nowadays we call it science. We can measure the details of this collision evolution. And basically what is important nowadays is that we know that the initial state is quite important and plays important role to describe various observables. And by the initial state, we basically can say what is the position of the nucleon inside the nucleus. And one can imagine that several nucleons from first ion could collide with one or with several nucleons from the other ion. And this may be different depending on the collision. So basically, event by event or collision by collision, the densities are fluctuating, and we know that they are fluctuating from nuclear physics. And in relativistic heavy ion physics, we also realize that this plays quite an important role in the description of the collision evolution. And this is what we call initial state. Then, for some amount of time, and what I'm supposed to mention is there are plenty of models that try to describe the initial state and how this initial state influences the whole evolution. There are a lot of topics. I just took some of the statements. They are not very modern. Some of those, at least color glass condensate, is not very modern, and I would, in my opinion, it is a sort of mostly vanished by now. However, what is interesting is that there are a lot of aspects of description of each stage of the collision. So for the initial state is basically what happens at the very beginning. What is the role of this positioning? What is the role of the energy density of these nucleons? Is it how much this depends on the collision energy and so on? Does it actually depends or not? and all of that is just a question for one single stage, but we can raise multiple questions for each stages, for each of the stages. Then what happens is there's also a so-called pre-equilibrium dynamics, which basically at this stage, a lot of hard scatterings happens, and there are a lot of non-trivial description, especially from theoretical point of view. What happens? How much time does it take to create pre-equilibrium dynamics? How much time does it take to go to the state of matter which we think is called quark-gluon matter or quark-gluon plasma? However, after this pre-equilibrium state, usually there are several theories which describe the quark-gluon matter, and most of these theories, they either say that the quark-gluon matter could be described as the hadron resonance gas, is a gas of basically particles, or there is a more complicated structure which involves so-called relativistic hydrodynamics. Basically, when we convert particles to the energy density, and then this energy density, then we try to apply equations from relativistic hydrodynamics to describe the evolution and the expansion of this matter, and then at some point we move to so-called hadronization. We convert this energy density or fluid cells into the particles. Basically, this is a hadronization stage, and then at some later stage, particles can also scatter for some time because there are plenty of particles and they're quite close in the phase space, and they scatter for some amount of time. And then they reach the moment when the particles just fly away and do not interact between each other anymore. And we can register those with our detectors. What is super important here is that actually different observables that we use in our field, they try to answer to various questions, basically addressing the questions to each of these phases that we discussed. Some of the observables are quite sensitive to the initial state. Some of those observables are quite sensitive to the hydrodynamic evolution. Some of those are sensitive to the hadronization, and some of those are sensitive to what happens at the so-called kinetic freeze-out. Or and what else I supposed to mention is that this hadronization we will call chemical freeze-out, and the latest is I will call kinetic freeze-out. And I just mentioned a few of types of the measurements that people can do, but there are actually quite more, and some of those are more sophisticated than the others. But I will try to talk about some of the topics that I think will not be covered over the next series of the talks. And just to introduce some definitions quite shortly, there is a so-called pseudorapidity or rapidity, which we define as an angle, basically an angle between the beam direction and the direction which is transverse to the beam. And pseudorapidity equals to 0 basically means that particle got emitted at the 90 degrees, basically perpendicular to the beam direction. Also, we will call azimuthal angle phi, which is an angle in the x-y plane, which is also sort of easy and quite similar to the school math that everyone does. And another thing which is quite important here, but I will not stop on the details of how people identify this or calibrate or measure the centrality, but that is an important measure of how strongly or how violent the collision was. And we will call peripheral collision the collision when two ions just a few nucleons collided, and we will use as a measure of this distance, we'll measure the distance between the centers of the ions, and we will call it impact parameter. So basically, for when this impact parameter is large, there's a peripheral collisions, and then when the impact parameter is small, we will call this collision types of the collisions central. And the red particles here are particles that interacted. We'll call them nucleon participants, and those which do not interact, we'll call them spectators or nucleon spectators, because they will fly away without any interaction, or at least we will not discuss the interaction between these nucleons in this talk. So now about the relativistic heavy ion collider, you have already heard, I think, a couple of weeks ago, but just want to remind you that there are several colliders, and each of them covers a lot of sort of energy range in which people would like to measure some properties, intrinsic properties of the quark-gluon matter. And the relativistic heavy ion collider started in the year 2000. With 4 experiments running, so Phoenix, Phobos, Brahms, and Star. Right now, only Star is operating, while this year the new experiment S-Phoenix, Super Phoenix, will start. And this experiment is supposed to keep running till 2026. And over the recent years, basically 22 years, there's a very interesting program was performed at this collider, and in particular, you can see the whole zoo of the ion species that have been collided at various energies. Not all of those at the same energies. However, we do have energies for multiple of those. And the most interesting for us is gold, because, you know, everyone loves gold, and this is very expensive material. So actually, we collide gold ions because they are large enough, and they are mostly spherical, almost spherical. And we can collide the ions either in the collider mode, when 2 beams are coming from opposite directions and they interact, and then the energy is quite large. This is from 7.7 to 200 GeV. And in the other case, we can insert a fixed target and go down with energy range to basically down to 3 GeV, center of mass energy. And this is so-called QCD phase diagram. When we collide ions, we can actually measure some properties of the collision, and one of the properties is the temperature, and another one is baryon chemical potential, which could be defined in the statistical mechanics, or also you can think about this baryon chemical potential as about baryon density, where for low baryon chemical potential, this low baryon chemical potential will correspond to the low baryon densities, basically LHC and top RHIC energies. At this high energies like 200 GeV, 2.76 TeV, tera-electron volts, almost all nucleons from the initial state got melted into the quarks and gluons. While going down in energy, we have less and less melting power. You can think about this, about melting power. And basically looking at this collision energies, we can map the phase diagram as a normal phase diagram. For instance, it's a phase diagram of water. And we can look at the properties of the quark-gluon matter, and there were plenty of measurements performed during Wimmer's Kanban program. And prior to that, we have identified that at high energies that indeed a quark-gluon plasma exists, and now we would like to know when when we collide nuclei at low energy, we know that there's no quark gluon plasma. It's a normal nuclear matter. At high energies, there's a quark gluon plasma, so we're supposed to find the area in which this transition happens. And there may be different types of the phase transitions which are involved in this evolution. And all of that, and in order to define the properties, we need to scan, perform the energy scan of the collisions and get understanding about the properties, intrinsic properties of the matter. And here I just want to mention that over the last 4 years, basically starting 2018 till 2021, there was a beam energy scan phase 2 program, which allowed us to go in the collider mode down to 7.7 GeV and increase statistics as compared to beam energy scan 1. So beam energy scan 1 is a gray bars here, and beam energy scan 2 is red bars here. And also we inserted fixed target that allowed us to get quite a lot of statistics at the lower energies and also in the several overlapping energies, which will help us to understand the properties of the expansion in the transverse plane and also in longitudinal directions and compare. So now, of course, the question comes: how does the nucleus look like when we collide those? And if you look at the nucleus, do we see actually the whole nucleus, or individual nucleons, or individual partons? And of course, the answer will depend on the collision energy. So the lower the collision energy, the less we can say transparent the nucleus is, and the more we have more quarks, and because of this we have higher baryon chemical potential, or higher baryon densities, while at very high energies basically we have almost equal amount of quarks and antiquarks, which leads to quite low mu b. We'll call it baryon chemical potential mu b, low mu b, or low baryon densities. And the STAR experiment nowadays looks like it's a typical collider experiment with time projection chamber, electromagnetic calorimeter, all of time of flight system. All of that is put into the magnetic field, in the huge magnet with a magnetic field of 0.5 Tesla. And in addition to the standard collision, we also inserted the thin target, which is basically the thickness of the target is 250 microns. There's a gold target, and we inserted in the beam pipe here basically a 2 meter and 10 centimeters at the end of the TPC, and then beam which is coming from the we call it yellow beam, which is coming from the west side, interacts with the target, and the produced particles are flying mostly in the forward direction. Some of those are flying at mid rapidity, but most of the particles, due to the kinematics, will go in the forward rapidities. And this is the reconstructed events from the event display during the data taken. This allows us to go to low energies, and there at low energies, because we have large baryon chemical potentials, actually a lot of ions could be also produced. And here you can see that STAR can perform very good particle identification, not just pions, kains, and protons and neutrons, but also we can do triton, helium-3, helium-4, helium-6, and basically up to lithium-7. And we can identify those particles or ions via ionization energy losses, or some of those we can also try to measure via the time of flight technique. Now, basically coming to the most important observables, I have already described the evolution of the collision, but what we want to know is what is the temperature of the collision, and at what temperatures the particles can be created, and when the basically chemical and kinetic freeze-out happens. During the chemical freeze-out, inelastic collisions stop, and we believe that inelastic collisions stop. And we also think that the particle yields, or basically particle species, are fixed and will not change anymore. And then because of, and this actually allows us to use statistical models to extract baryon chemical potential and temperature at kinetic freeze-out. And in addition to that, we can measure the particle spectra, and looking at the particle spectra, we can also, by particle spectra, I mean transverse momentum of the particles. We can measure temperature at which particles on average stop interacting, and what is the expansion velocity. So basically, this means that measuring the particle yields, their ratio and their ratios provide an extremely important information about the QCD phase diagram and about properties such as temperature, baryon chemical potential, and expansion speed or expansion velocity. So how do we measure this? We actually measure for each type of the particle, we measure transverse momentum spectrum and quite a broad momentum range. And here I would like to mention that you can see that the various colors and markers correspond to different centralities. And this is important because one can think about the system size for the most central collisions when the system is large. One may expect that the temperature will be large, while at smaller, at more peripheral collisions, one may expect that the temperatures will be lower, and we can actually test this looking at the particle spectra. Once one build the particle spectra, we can integrate over the PT range, and this will provide us the yields, basically how many pions, how many kaons, how many protons, how many antiprotons, and so on we have. And what we can do then, we can normalize this yield to the average number of participating nucleons, basically number of nucleons from the initial state that interacted. This is a model-dependent estimation, unfortunately. Usually people use Glauber model, Glauber Monte Carlo to estimate number of participants and number of binary collisions that happen at the very early stage. But this basically means how many this particular observable means how many particles of the given sort or of the given species have been produced per single nucleon collision. And here what you can see is that this is a particular plot for 14.5 GeV, but what is interesting, this is an energy dependence. So the triangles here at the top for pions, kaons, and the others, those are 200 GeV energy collision energies. And the very bottom, the circles correspond to 7.7 GeV. So you can see the clear trend over here. And the higher basically the energy, the collision energies, the more yields we have, because we basically insert more energy in the system. And when we have more energy and more particles, we can convert, because, you know, there's a famous Einstein equation, energy equals to energy square equals to momentum square plus mass square. So basically, the more energy we have, the more particles we may create. assuming that the momentum will stay in the average. It will not change much. And what we see that indeed there's also this n part on x-axis corresponds to this the collision centrality. So this when a few nucleons interacted, this is a peripheral collisions, and the more nucleons interacted, so central collisions. And basically, you can see that there's increase of yields from peripheral to central collisions, except for antiprotons, which is interesting. However, the uncertainty, you can also see that the uncertainties are not quite small, but overall there's similar dependence. And also for antiprotons, it is a bit different because antiprotons could be only directly produced, and we have a lot of antiprotons at high energies, and not many at low energies. While for protons, it's not so trivial dependence, because if you can look at this, follow my pointer, you can see that the circles are quite above triangles, which are somewhere here in the middle, and this means that at low energies, the internal or initial nucleons could be propagated to the final state, and we not just measure produced protons, but we also have some protons which are coming from the initial state, and that is an important thing to remember. And then when now we know about the yields, we can look at this picture as an energy trend from very low energies, like from AGS, starting from AGS to ALICE, to the very high energies at the LHC. And for pions, you can see that on average, there is a sort of an increase of the yields with some step here around basically 15 to 20 GeV. There's a very interesting and intriguing dependence. Is a difference in the positively and negatively charged KN yields. And original expectation from like 25 years ago, or even before that, was that this difference could be explained by the existence of the core gluon plasma, or when it just appears, then it means there will be a difference in the an enhanced production of strange particles. However, some of the modern models can describe this behavior when introduce more particle resonances, and when they introduce specific processes like associated production. And you can see also the clear trend between number of yields of protons and antiprotons. Basically, antiprotons increase the yield and almost going to almost to a plateau here, while for protons there's a decrease. But what is very important for most types of the particles, for pions, kaons, and protons, basically starting from 200 GeV or even before that, all of these types of particles, they start being produced symmetrically. Basically, how many positively charged pions produce, so almost the same amount of negatively charged pions will be produced. Same for kaons and protons and antiprotons. You can see that basically at some point they start to be produced symmetrically. Now, if you want to extract the temperature and baryon chemical potential, now when we know how to estimate yields, we actually measure yields for a huge amount of particles, and then one of the approaches, what people do, they use so-called grand canonical ensemble, which is quite well known from the statistical mechanics. We assume that there's a hadron gas in a certain volume with a certain temperature, and then we can create a partition function with some definitions over here, and then basically we can estimate by varying the baryon chemical potential and temperature, we can estimate the yields of each sort of the particle and extract the parameters such as temperature and baryon chemical potential. Another part which is important, we can also look at this particle spectra, basically pi kp spectra, because this is most of the particles, and we can apply so-called blast wave model. We can feed the spectra with this blast wave model, blast wave actually parameterization, which assumes that the system expands with some collective flow velocity, and then we can, at some point, we can emit particle from basically from the surface of this blast wave at some certain temperature and with a common transverse radial flow velocity. And basically, this simple model, which is shown here, could be used to feed the spectra and extract temperature and flow velocity. Basic flow velocity is basically, you can think about the velocity of the expansion, system expansion. And then here, this is the how we map the QCD phase diagram, and you can actually see that for each collision energy centrality, we have a dependence of the temperature with respect to baryon chemical potential, and this is how people usually measure these observables for chemical freeze out. Yeah, somehow I just inserted the same figure twice, but sorry for that. And also we can extract the dependence of temperature at the kinetic freeze out with the expansion velocity, and the temperature actually increases from central to peripheral collisions. This is one interesting and important. This is a peripheral. This points correspond to peripheral collisions. This is for the central collisions. So the more violent collision is, the faster system expands, while for the peripheral collisions it expands slower. And there is a sort of an energy dependence, but it's not collision energy dependent, but it's not quite dramatic as one could think about. However, the more changes happen at lower energies, because the baryon chemical potential changes drastically when we go to the energies below 20 GeV, okay, 10 GeV. Each 100 MeV in the collision energy may be converted in tens or even hundreds MeV of baryon chemical potential, while it is not the same for the high collision energies. And then we can also look at all of these curves all together and look at the world data that we have. And here the top curve corresponds to the so-called chemical freeze out, meaning that standard particles like pions, kaons, and protons cannot be produced at higher temperatures because temperature is too high, meaning that the partons will move too fast in order to create the nucleons. Basically, temperature is too large to create anything except quarks and gluons. While the kinetic freeze out even goes down a little bit, and this is due to the longer interactions, elastic scatterings that happen at the late stage. So basically, system has enough time to cool down a bit. But overall, both of the trends intercept somewhere at around 7.7 GeV. So it means that we really need to measure this area between 15 GeV down to like several GeV in order to have a precise measurement. And we also, in the velocity profile, what you can see is that there's a sort of a plateau, which may suggest that there's a change in the in the behavior of the system. It may suggest that there's something like change of the phase transition, which we know, for instance, for the water or for some other substances. Okay, what else do we know from the, actually, I need to speed up quite much. What else do we know? For example, in PP collisions, we know that the so-called jets that are produced, there's one, a trigger jet, which has the partons with very high momentum, and then this will be a trigger jet or leading jet, and then there will be associated particle, associated jet, which will go in a backward direction. Here, the selection will perform such that trigger particles were selected in the high PT, while the associated particle was also with high momentum, but basically looking, but not very low momentum. And what is interesting here, what you can see is that most of the some of the particles near the leading or trigger particle will go in the delta phi. Now we're looking at the transverse plane, will be grouped together here, while the other guys will go at the basically pi radian, 180 degrees, basically flying back. This is a back-to-back scattering. This is a standard thing, what we know from PP collisions. But now this is one of the new property that was one of the proof of the QGP existence, is that when people started looking at the gold-gold collisions and compared it to PP collisions. For peripheral collisions, you can see there's a slight suppression in the backward direction, while in the forward, while the central or the trigger particle, there's not much difference with PP. While in the central collisions, again, not a big difference in the trigger particle, but a dramatic difference in the backward direction, which means that there's a jet suppression, saying this the trigger particle is flying away easily, while the produced particles supposed to fly in the backward direction, they got suppressed due to the interaction inside the quark gluon plasma. If it would be a standard hadron gas, this wouldn't be such. Basically, particles would be produced and go through the matter almost without interactions. And this means that the quark gluon plasma is a different state of matter with respect to the normal nuclear matter. And that was also cross-checked almost 20 years ago by measuring the difference of the pi zero yields, neutral pi yields, when people compared yields in gold-gold collisions to the yields in PP or to deuteron-gold collisions, and renormalize it to a number of binary collisions or binary interactions. And what you can see that for gold-gold collisions, for central gold-gold collisions, huge suppression with respect to proton collisions, while for deuteron gold collisions, which is a slightly smaller system, there is almost no suppression. Again, that hints us that in large systems the QGP exists, while it may not be true for small colliding systems. And then people start searching or looking for the CERN-off signatures of QGP. People start looking at the so-called ratio of the yields from central to peripheral collisions, because due to the technical limitations, accelerators cannot always accelerate the same types of particles and the same different types of particles at the same collision energy. And because of that, one of the natural choice was compare central collisions to peripheral collisions, applying the proper renormalization to the number of interacted nucleons, and measured and performed a set of measurements for charged hadrons here and for pions, kaons, and protons, And what is interesting is that somewhere around 27 GeV or 19.6 GeV, one can see that the change between the suppression to the enhancement happens, which is maybe an interesting observation. However, you can see the bars here, and these bars are our limitations, which very hard to minimize, and these limitations come from our understanding of the centrality of the collision. So basically, how many nucleons interacted in central and peripheral collisions, and this is extra uncertainty that we have to keep in mind. Basically, the picture is quite similar for various types of particles, but we need to have more particles and more collision energies with high statistics in order to make a precise measurement and understanding what is going on there. Now I will have to, I think, speed up even more, even though you will have the discussion on this particular topic quite soon. Another thing is what is the other global observable happens, and this is the definition of so-called reaction plane when we have two nuclei which are incoming. So basically, with two beams, we have already introduced impact parameter, which connects the centers of two ions, and then we can define the plane, which will be set up by the beam direction and the impact parameter between two ions, and then we can actually decompose that. It was proposed, I didn't put the reference here, by Sergei Voloshin. This is the most famous and most standard definition of this decomposition nowadays. In past, people use different decompositions, but it was hard to compare between the experiments. Well, nowadays, this is the most standard one, which is called flow measurements. And one can decompose anisotropy with respect, momentum anisotropy with respect to this reaction plane. This reaction plane, basically initial geometrical anisotropy due to the collision, due to the pressure gradients, will lead to the momentum anisotropies. And we can measure this momentum anisotropies and look at the various Fourier components of these anisotropies to extract different physics. For example, this is V1, which is called directed flow, describes the sideward collective motion of particles in XZ plane. There's also a very famous V2, which is called elliptic flow, which is sensitive to the properties of the medium. And there are actually many more terms of this decomposition. The higher the order, the more sensitive it will be to the initial state and to some other properties. But the higher the order, the more complicated it will be to measure the observable. And what is interesting here, theory actually predicts that if one measures this directed flow, that there will be a specific minimum as the collision energy, and this minimum will correspond, supposed to correspond to the first order phase transition. And this is one of the things that people start looking at. And most of the measurements actually suggest that basically baryons have such a minimum, and they go from almost zero to positive values, while mesons all have negative values and go down, but also anti-baryons also go down. So this complicates the situation. However, it also suggests that another important thing that we probably do not catch in the models. And we need to measure these anisotropies in order to extract what happens within the collision. And one of the options was to measure these pressure gradients. We could decompose, we can measure the single particle here, for example, anti-lambda, and then we tested so-called quark coalescence, or coalescence sum rule for the quarks. With this assumptions, this directed flow is developed at the prehadronic stage. Specific quarks have same directed flow, and hadrons are formed via coalescence. And then we can basically build anti-lambda from K minus, which consists of anti-U S quark, and 1/3 of anti-proton, which consists of anti-U, and anti-D quark. And then you can see that they actually agree with each other quite well, except 11.5 GeV, where this difference is depicted here becomes dramatic, which means that at least one of these assumptions is not correct anymore. This is also an interesting observable to look at. Somewhat similar people can do with the elliptic flow, and measuring all of those types of particles. You can see there's a mess out there. However, in the case of one assumes a proper scaling, also basically number of constituent quark scaling, we can redo that for high momentum particles. Actually, almost all mesons and baryons got grouped into some specific order at high momentum, and if one performs the sort of a scaling and takes into account the amount of quarks within baryon and the meson, then all of those could be lined up into almost the same curve. And it is also interesting to look at such things across the energies, because it may suggest us when the properties of the matter change. If you don't mind, I have like a few more slides and two topics, but they're quite interesting. One of them is the vertical motion of nuclear matter, which is quite a new phenomenon in the sense of the measurements. Even though it was proposed to be measured many years ago, we didn't have enough statistics to perform an accurate measurement. And nowadays, at RHIC and the LHC, we do have enough statistics to do that. Basically, when we collide two ions, you can see that there's different pressure gradients, and the whole system may follow the vertical motion, which could be easily described as this equation. And it could be connected to the so-called relativistic vorticity. In other words, the whole system, because of the non-central collision, may have an angular momentum which will be distributed between the particles, and such a thing is supposed to lead to a so-called spin polarization. And somewhat similar effect was observed many more than 100 years ago, when and this was called the Barnett effect, when people that was describing the magnetization of the basically object by rotation. So such a polarization could be measured. I will talk only about the so-called global polarization of lambda hyperons, because it's much easier to imagine and to understand. So on average, if you will look at this picture, particles will be emitted in all the directions, and there is no good direction to look at, except if you know that there's some particle which is already polarized, and we can extract this compare this polarization on average. So on average, all the particles will be polarized, but not all the particles will keep the same polarization. And lambda hyperon, due to the weak decay, due to the weak interaction, spin of the lambda hyperon will be transferred to the spin of the daughter proton, and then we can look at the angular distribution of the daughter proton with respect to this, again, reaction plane. This reaction plane is super important in our field. And then we can look at this sine term with respect to the reaction plane, averaging over the events, and this is what we will call the global polarization. And recent measurements, so this first 2 points here, at 62 GeV, 200 GeV, these are the old measures from 2007, and you can see that the uncertainties were quite large. And then the recent discovery in 2017 was published in Nature, suggested that actually there's a non-zero polarization, and this polarization grows, going down in energy and not in opposite direction, which is sort of surprising, and it is already quite an important new phenomenon in the field, and a lot of models try to introduce this polarization right now. And there are plenty more measurements have been performed. So we have this reaction plane, and then we can measure the polarization. This is the old polarization measurements that I have, old, I mean, from 2017. Then more new particles have been added, at least to high energies, to 100 GeV. And also there is an energy point recently published by Alice in 2020. So basically you can see that at high energy, the polarization is almost zero. While it grows when going down in energy, it will be very interesting to look what happens there. We have already measured the polarization 3 GeV, which is quite large. So I suppose to actually put the point here, but it would be somewhere around 5% or 7%. 5 to 7, yeah, I think about 5% here, 3 GeV. And it doesn't drop down, and it's not actually obvious from the theoretical point of view if it will grow infinitely or at some point it should drop. And one of the things that I want to mention, so for 3 GeV, there's some theoretical predictions that work okay, but in general, global polarization could be described in the models, but only when you work hard on the model and tune it specifically to measure the polarization. Overall, this is the global polarization, but there are other types of polarization that could be measured with respect to different symmetry planes, and those actually do not match between the experiment and theory. Mostly do not match, which means that people need to tune theory in order to describe the data. And the last part, I will not actually, let me not to stop on the details of how people measure that, except saying that one thing that people can also try to look at is at the correlation, momentum correlation, correlations between the particles, either just a pure momentum correlations or momentum correlations with respect to the, again, reaction plane or event plane. And this will provide an important thing, because when people measure such correlations, the correlation functions, the width of this correlation function will be inversely proportional to the emitting source radius, with the source size, and in general. And then using some decompositions, one can actually access non-trivial dimensions, not just the spatial sizes, but also time scales, like what is the maximum time of the maximum emission, what is the actual time from the beginning of the collision to the time when the maximum emission of particles happened, and what was the duration of this particle emission. And those are quite important constraints on the models, and these time scales will be extremely sensitive to the changes of the phase transition types. This is just a sketch of how important those measurements are altogether with, for example, flow measurements. And the points here are experimental data, while the curves are different theoretical predictions before the measurements and after the measurements altogether. So in other words, this is extremely important to measure the spatial dimensions in order to constrain the models. Only, for example, spectra and flow are not sufficient enough to provide the constraint, and this so-called syntoscopic radii are one of the strongest constraints on the theoretical models. And it is actually the other side, the dark side of the story, is that actually it is hard to introduce this radii into the models. So it's really need a lot of efforts from theorists to do that. And basically, this is my pre-last slide. So this special radii, femtoscopic radii, have been measured as a function of collision energy. And there are two important and interesting things occurred. First of all, this ratio of two of the three components is supposed to be quite sensitive. Ratio, or the differences of the squares, are quite sensitive to the phase transition types. And in case of the first of the phase transition, there are supposed to be huge delays in the particle emission process. And because of these delays, this ratio or this difference is supposed to grow up. And in case of the normal explosive expansion, which we call crossover phase transition, those supposed to be those values supposed to be quite small. Indeed, looking at this overall picture, one can actually look at this ratios and these differences precisely. And there's you can see excitation function, which shows that there's indeed a peaky structure, which peaks somewhere around 30 GeV, which is quite interesting and intriguing. But this measurement has been done only with pions, so it is very important to do other particle species in order to look at the changes of the phase transition. And another thing which was realized and published recently, here I somehow didn't update it was already published. I didn't somehow modify the link to the archive. So we can look at this R side is a transverse size, and R ln is longitudinal size of the particle emitting agent. And what is interesting, if one looks as a collision energy, so at high collision energies, this means that expansion goes in plane, in reaction plane, while at low collision energies, it goes perpendicular, or basically so-called out of plane expansion. And this could be easily explained by the fact that at low energies, the passing time of ions is so large, it may have, the duration may go up to tens of Fermi over C, while at LHC energies is basically 0.1 or 0.01 Fermi over C. So basically spectator nucleons, they do not allow particles to be emitted in plane, and the only thing that the direction that is allowed is to emit particles outside or out of plane, perpendicular to the reaction plane. And this is a very interesting observation. It would be extremely important to measure this plot. And as you can see, this magenta points, all of those points, at least for now, and this red point are the measurements from STAR. There are a lot of measurements here. Also, you can see the energy energy dependence, but most of this energy region have been measured quite precisely by STAR. And also there's an interesting point by Alice, which is also important, and new measurements have much less statistical uncertainties, but still you can see that the overall excitation function has a quite good mapping from STAR. And this leads me to the summary. I would like to say that there are a lot of exciting results and measurements performed by STAR, by the STAR experiment at mid energies, basically from 7.7 to 200 GeV. And there are a lot of new results from the beam energy scan program when we took much more data in the region from 3 GeV to 19.6 GeV or 27 GeV. And there are quite many observables, and to look at those observables, one always need to keep in mind that the collision centrality measure is quite important. Event plane or reaction plane measure is quite important. Particle momentum measurement is super important, and also the particle identification. All of this together, when we have all this information, we can construct various types of the observables, like anisotropy measurements, particle spectra, flow measurements, femtoscopic measurements, global polarization measurements, all of that depend on this basically important 4 steps, and then one can do a lot of measurements, and the only limitation that we have is our imagination. Okay, thank you for your attention.
Thanks, Grigory, for this nice talk. So the session is now open for questions. So please feel free to raise your hand or unmute and just ask. Meanwhile, maybe I can ask a few questions. So, so you mentioned that this proxy for the impact parameter has multiplicity, right?
Mm-hmm.
While doing the centrality determination. So I was just wondering that whether there can be other observables as well, like, for example, transverse energy or spectators in ZDC, or say net charge.
Yeah, that is an absolutely great question, and the answer is yes. The centrality, I was not actually. STAR uses several definitions of the collision centrality, depending on physics. But overall, for example, the collision centrality could be standardly, we measure it as a function of multiplicity inside TPC. And that is because we understand that at high energies, number of produced charged particles could be well represented by a convolution, basically, of the negative binomial distribution with number of participating nucleons, number of binary collisions, which could be described by the Glauber model. And at mid-rapidity, we have quite good efficiency, detector efficiency, registration efficiency, and this is the standard approach. Another option could be to measure the transverse energy, which would be a proxy for the number of collided, basically, nucleons. And then, once again, one will need to convert the transverse energy to the number of collided nucleons with some approximation. And likely you will use, again, the number of the Glauber model or something like this. Another option that was actually used in past, people tried to correlate number of particles produced at mid-rapidity with the energy deposition in the forward detectors like BBCs, or even 0-degree calorimeters at the which are quite far from the center, nominal center of the TPC, for example. And those correlations are also important and unique. However, at some point for STAR, we actually decided it's probably not extremely important for all the types of the measurements, and we also do not have quite good precision of the resolution in the forward direction. I mean, in ZDCs, because we do not have a very granular ZDC. However, nowadays, we also did the same stuff with BBCs. It's a beam counters. It's a plastic, basically, you can think about that as a hexagonal detectors. The granularity is not good, was not good. But starting 2018, STAR performed several updates, and now we have event plane detector, which is high granular scintillator, which allows one to measure basically extract amount of particles which are going in a forward direction. And that is, we are working hard on adding this particular measurement into the centrality. It's also a bit tricky because for low energies, we are still testing how valid the Glauber assumption is. But I hope that answer to your question will be, of course, there will be many measurements depending also on the detector setup. For most of the measurements, collider experiments use number of charged particles. and correlation number of charged particles in the central region, or energy deposition in central region, one can actually imagine multiple definitions of the same quantities. But for example, for the fixed target experiments, it will be more convenient to look at the forward direction where all the particles are flying, and calculate energy deposition or number of charged particles in the forward direction, and then one can actually recalculate it back to the collision centrality. Of course, the more particles interacted, if you have a central, if nuclei collided in a central way, there will be only particles produced in the forward direction, but they will have very specific patterns. However, if it was a peripheral collision, then spectators will fly in the forward direction and will hit the detectors and deposit a lot of energy because of the peripheral collisions. Yeah, so there are several ways of constructing these things. In principle, we looked at the correlations, and at some point, STAR decided that we will, for most of the measurements, we will use just number of charged particles at mid rapidity. While for some very specific measurements that I believe you will have people who will talk about fluctuation analysis. We redefine this particles. We are looking not just at the charged particles, but we can look at the charged particles except, for example, protons and antiprotons. And this we need in order not to perform, the bias, or not to introduce the bias to the measurement. Yeah. This really depends on what physics you want to extract. For the 90% of the standard physics analysis, we would like to use just the number of charged particles produced.
Okay. Rishi, you have a follow-up question to this? Maybe you can ask.
Okay, yeah. So it's related to what you were saying. So can you alluded to this fact that you connect dm charge by deta to centrality by some sort of a Glauber model. So you have something like dm charge by deta equals to some C1 times n participants plus C2 times n binary, and then you fit C1 and C2. And given that dm charge by deta distributions are presumably quite different at different temperatures, what do? Do you just do a different fit of C1 and C2 at each root S, and then that defines your n part for each of them? Is that how it's done, or there are some other effects included in the Glauber?
Yeah, that's an extremely valuable question, especially for low energies. For high energies, this is quite simple, right? We have this two-component model, which has n part and n call, with some special factor which accounts for the number of hard scatterings, or number of hard processes, fraction of hard processes. And then we basically fit the measured multiplicity distribution we just calculate n part and n call, and then we try to match n part and n call and number of particles generated by the negative binomial distribution. We just match the experimentally measured multiplicity with that one. For low energies, for lower energies, we actually looked at this in various ways. And in the collider mode, we do not see big effects. And probably the reason is that at 7.7 GeV, we still have energy which is large enough to follow the standard trend, to follow Glauber Monte Carlo. However, at lower energies, like 3 GeV in the fixed target here, we had to redefine the multiplicity that we use to calculate centrality. Now, if in past we calculate number of tracks, so-called primary tracks, which originate from the collision at mid rapidity, we calculated those with some certain, quality of the reconstruction. Now we had to recalculate the quantity, and we assume only primary particles which originate from the fixed target, not from anywhere else, but from the fixed target, basic number of primary tracks. And that is one thing. Basically, now we are looking at the forward direction, not just at mid rapidity, but also at the somewhat like at the forward direction. This is one principal difference or general difference between the collider and fixed target mode that we have in STAR. The second part is how well do we define centrality and how well do we understand end part and end call. This is actually two different questions, because understanding of centrality is basically how well do we measure multiplicities, and in principle nowadays we have a quite good not just detector, but also trigger logic. And the only reason why we need Glauber at most of the energies is to take into account the trigger inefficiencies in peripheral collisions. For central collisions, basically from 0 to 20%, we are very, very sure that our trigger is 100% efficient. And then go into more peripheral collisions, the efficiency goes down, the trigger efficiency goes down, and only for the most peripheral collisions it drops. So basically, our trigger efficiency is not good for the centralities from 65% to 80%. Central collisions. For the central collisions, we are golden. Everything is fine. Now the question is, how well can we calculate? This is still the first question. How well do we understand centrality? And in principle, we can actually cut the multiplicity distribution using Glauber or whatever other model, or even without any models, by looking at the integrals, and have a quite good precision in the centrality percentile. That is the answer to the first part of the question. The second part of the question is actually quite complicated, and we are still working on this. The second part of the question is how well do I understand end part, number of participating nucleons, and number of binary collisions at low energies. And that is very, very non-trivial, because when we try to calculate, we use the Glauber, and actually there's also a Hades experiment which is operating even at the lower root S, basically 2.3 GeV, as far as I remember. They actually try to compare the Glauber calculations and also EuroQMD calculations for centrality, and they came to the conclusion that in principle EuroQMD is a bit better, but overall they came also as STAR, they said, okay, centrality is fine, but number of participants, there's a problem. When one goes with the Glauber and then tries to compare, for example, the yields, because that we believe we know the conservation laws, like the baryon number conservation, charge conservation, strangeness conservation, and look at the yields of the particles. What happens is that actually we do not we integrate the yields into 4 pi. Then Glauber does not underestimates. Okay, Glauber model underestimates number of participants and number of binary number of participants. This is the most important thing, and that was a shocking thing. So we can estimate centrality quite well, but then we underestimate number of participants within the Glauber model at low energies. Then the other thing that we are still working on this understanding. So the second part was try to use for example, your QMD model and try to calculate the same thing. And here again, the problem, or not a problem, it looks like your QMD does a much better job as compared to the Glauber. However, at least in our calculations, it still underestimates the expected number of participants, but it is much better as compared to the Glauber. I'm not saying the numbers because this work is still ongoing. So basically, centrality is fine. The number of participants or any type of the observables, which could be or should be scaled with number of participants, that particular thing is still, we are still working on that part, because n part or number of participants is not a super obvious thing, what is the most proper way to calculate. And then also there are a lot of other assumptions that may not work properly anymore at low energies. For example, Glauber assumes that there is no elastic collisions. Okay, only inelastic collisions are taken into account, but at low collision energies, elastic cross section becomes large. So basically, at some point they are almost comparable. I mean, inelastic and elastic collision cross section, nuclear cross section, and that means that one has to be very careful. And some of the Glauber assumptions do not work properly anymore. So I'm not sure if I have answered your question completely, but in general, once again, 2 points. Centrality definition is okay. There's no big problem with that, but estimating number of participants at low energies is not a trivial task. We are still working on that.
Okay, thanks a lot.
So, so you think instead of multiplicity, looking at a conserved quantity like say net charge, can it be better, particularly at lower energy where you have fair enough, large enough rapidity coverage to look at the entirely produced net charge? Because that would be directly the proton participant, right?
Not exactly. The problem is that with the net charge, so we have positively and negatively charged particles produced. At low energies, if at high energies, most of the particles are pions, at low energies, it's not true anymore. And there are some of the charged particles may be pions, and almost like a third or a half of those will be protons. And some of those protons may come from the initial collision. And basically, the scatterings may be so large that this initial protons may actually scatter almost like perpendicularly to the initial direction of the beam. So it's not, so the net charge.
But that's still a participant, right?
Right.
When you are wanting to estimate n part.
Right. But the question is, how many times does this participant interact? And that's not a trivial thing.
Okay.
Because of this large scattering angles and due to the large elastic scatterings, actually initial nucleon may scatter at almost like 90 degrees or at large angles, and then interact several times or scatter several times, because the probability, basically the cross sections of elastic and inelastic collisions at low energies are almost the same. So it is not actually trivial how to count this inelastic collisions, or sorry, this elastic collisions in the models. I mean, probably some dynamical models like your QMD already has some implementation, but I do not know the details of this part of your QMD, unfortunately. But that's indeed not a trivial thing. Another thing that one has to keep in mind that in principle, such scatterings, a lot of momentum could be transferred. And for example, we have, let's assume that we have 10 GeV nucleon, and then it elastically scatters and loses like half of the energy. And then basically the next time when it will interact next time, basically we will need to modify cross-section, which we put into the Glauber, for example. And that is also a kind of a dynamical recalculation, which Glauber knows nothing about, right? That is really not a trivial thing to do. Basically, one may need to think about either doing a real dynamical model. This is probably the reason why your QMD describes N part better than the pure Glauber.
Okay, thanks a lot, Grigory. So are there any more questions? We are already 1.5 hours into this session. Are there more questions? If there are questions, please unmute and you could ask. Meanwhile, Rishi, do you think we can stop the recording now? And if there are some questions.